You ever hear a weather forecast say there's a 30% chance of rain and wonder, what does that actually mean? Or flip a coin and think about the odds? Well, today, we're going to crack that code of chance because we're diving deep into the world of probability.
Look, our lives are just filled with these little moments of uncertainty, right? We're always trying to figure out the odds. But what if you could do more than just guess? What if you had a toolkit to actually calculate the chances and see the world a bit more clearly? Well, that's exactly what we're going to build together right now.
So, here's our game plan. First, we'll learn the basic language of chance. Then, we'll get into the real tools, the rules for calculating or and probabilities. And finally, we'll wrap up by looking at why this is such a practical, powerful skill to have.
Okay, first things first. Before we can start doing any of the fun calculations, we've got to make sure we're all speaking the same language. So let's learn the fundamental vocabulary of probability.
It all starts with this one core idea. Probability is really just a number between 0 and 1 that tells us how likely something is to happen. Think of it like a scale. If the probability is 0, there's no way. It's impossible. If it's 1, it's an absolute sure thing.
Now, to figure out any probability, you first have to know everything that could possibly happen. That complete list of every single potential outcome. That's what we call the sample space.
And an event is just the specific thing we're interested in. Out of all the things in our sample space, the event is the outcome, or maybe group of outcomes, that we're actually rooting for.
This slide shows it perfectly. Look, for a coin toss, the sample space is simple. Heads, tails. That's it. Nothing else can happen. For rolling a standard 6-sided die, it's every number from 1 through 6. Having this complete list is our foundation for everything else.
And here's where it starts to get a little more interesting. What if you have a family with 3 kids? You might think there are only a few combinations, but when you map out every single possibility, you see there are actually 8 distinct outcomes, from all boys to all girls and every mix in between. Listing them all out gives us that complete sample space.
All right, now that we've got the lingo down, we can finally put it to use. Let's grab our first tool from the toolkit, the classical formula for calculating basic odds.
This right here is the engine that drives all of probability. And it sounds a little technical, but it is so simple. All it's saying is this: the chance of something happening is the number of ways you can win divided by the total number of ways things could turn out. It's just what you want over what's possible.
So let's put that formula into action right now. Let's go back to our family with 3 kids. What's the probability of having exactly 2 girls? Well, we just look at our sample space and count the wins. There's GGB, GBG, and BGG. So that's 3 outcomes we want. We divide that by the 8 total possibilities, and there's our answer. 3 out of 8. Simple as that.
Okay, things are about to get a little more complex. What happens when we want to know the probability of one thing or another thing happening? For that, we need a new tool called the addition rule.
And the very first, most critical question you have to ask is this: can these 2 things happen at the same time? For instance, if you roll a die once, you can't get a 2 and a 3. It's impossible. So we call those mutually exclusive. But could you draw a single card from a deck that is a king and a heart? Yeah, you could, the king of hearts. So those are not mutually exclusive. Getting this right is key.
Now, for those mutually exclusive events, the ones that absolutely cannot happen together, the rule is incredibly easy. To find the probability of one or the other, you just add their individual probabilities together. That's it.
And this donut example is perfect. You're picking one donut. It can be glazed or it can be chocolate. But in this case, it can't be both. They're mutually exclusive. So we just take the probability of grabbing a glazed, that's 3 out of 12, and add it to the probability of grabbing a chocolate, 5 out of 12. Add them up, and you get 8 out of 12.
But what if the events can overlap? Well, if we just add them up, we're going to count that overlap twice. We don't want to do that. So the rule is add the probability of A, add the probability of B, and then, this is the crucial part, subtract the probability of the overlap, so it only gets counted once.
This medical staff example shows exactly why that's so important. We want the probability of picking someone who is a nurse or a male. So we add the probability of being a nurse, 8 out of 13, to the probability of being male, 3 out of 13. But wait a minute, one of those staff members is a male nurse. He just got counted in both groups, so we have to subtract that one person who's in the overlap to get the correct answer. Okay, we've handled the or questions, so now let's tackle and questions. What's the probability of one thing happening and then a second thing happening right after?
For this, we need the multiplication rule.
And just like last time, we've got a really important question to ask first. Are these events independent? In other words, does the outcome of the first thing change the odds for the second thing? You know, flipping a coin doesn't affect the next flip at all. That's independent. But drawing a card from a deck and not putting it back, that definitely changes the deck for the next draw. That's a dependent event.
So, for those independent events where one outcome has no memory and doesn't affect the next, the rule is super simple. You just multiply their individual probabilities together. Here's the classic example. The coin doesn't care what the die does, and the die doesn't care about the coin. They're independent. So we find the probability of getting ahead, that's 1 in 2, and the probability of rolling a 4, that's 1 in 6, and we just multiply them. 1/2 times 1/6 gives us a 1 in 12 chance of both of those things happening.
But for dependent events, things get a little trickier. We still multiply, but we have to adjust the odds for that second event. Basically, we multiply the probability of the first event happening by the new probability of the second event now that the world has changed just a little bit.
Take a look at this crime data. The probability of the first case we pick being from 2004 is 16 out of 53, okay? But once we pick that case and we don't put it back, what's the chance the second case is also from 2004? Well, now there are only 15 of those cases left, and only 52 total cases. The odds have changed, so we have to multiply our first probability, 16 over 53, by that new, updated probability, 15 over 52. So let's just step back for a second and take a look at the really powerful toolkit that we've just put together. You've got the basic formula to figure out how likely something is. You've got the addition rule to handle this or that questions, and you've got the multiplication rule to solve this and that questions. These are the fundamental rules.
At the end of the day, this isn't just some abstract math. This is a framework for thinking clearly about a really uncertain world. I mean, this is the logic that's behind insurance, behind medical tests, even the stock market. You now have the tools to go beyond just guessing and start actually calculating the odds. So my question for you is, what odds will you calculate first?